pleasure is double. First is I have to speak at around 4 o'clock in the morning on my time. And the other, I have a son here, so it's a pleasure to come to see him with other friends, new friends. And it was very nice. So the moment that we entered the department, started to speak physics. So wherever, this is one of the wonderful things of the world of physics. Wherever you go, you just enter an office and you start doing something. It's really lovely. So what I want to do today is tell you about some recent work and some less recent work about the mechanical yield in amorphous solids, and this work that was done together with Giorgio Parisi in Rome, with my postdoc Corrado Rainone, who was before a student of Giorgio, and a postdoc from India, YC. And let me introduce it, assuming that you know very little about the subject. So the general issue has to do with glass phenomenology and existence. I will explain. Okay. Everything will be explained. But you are most welcome to stop me any moment that I forget explaining something. So glass phenomenology. Glasses appear when you cool down liquids. And this is a typical phase diagram of a specific volume as a function of temperature of a material, which if you have the temperature sufficiently high, the material is in form of a liquid. For example, water. You cool down, there is typically a point that is known as the point of the phase transition, where the system, if you cool it slow enough, will crystallize and will give you a solid, a crystalline solid. From that point on, if you cool further, you just get a crystal, just with the slope of the specific volume as a function of temperatures that is smaller than the one you have in the liquid. It's less compressible. Nevertheless, many liquids, it's not a very rare phenomenon. When you go down sufficiently fast, you avoid the phase transition, and you get into a state that is known as a supercooled regime, where the system is no longer in thermodynamic equilibrium. The thermodynamic equilibrium is there, but when you cool down, it gets more and more slow in responses, and eventually you get materials like those that we know, like the window glass, polymeric glass, ceramics, all these things that are actually solids in the sense that what is the difference between a liquid and a solid? The liquid is a material that you put any stress, it will flow. A solid, when you put a stress, will react elastically and will not flow, at least for small strains or stresses. Now, the point where this is becoming a solid for practical purposes, in the sense that it's a solid on a human time scale, it could be sometimes reaching the thermodynamic equilibrium if you give it enough time. For example, we know in Israel, for example, you find Roman glasses, and the Roman glasses sometimes have crystallized. So if you give them 2,000 years, sometimes they will crystallize. But, we're talking about laboratory time scales. No experimental is waiting for 2,000 years. So the thing is a solid that is not crystalline, but is amorphous as the mother liquid which it came from, but it reacts as a solid. Now, this point where it becomes so is known as the glass transition. But the glass transition is not a very well-defined transition for the problem. If you quench or if you go slower in this supercooled regime, you go deeper into the supercooled, and then you get a glass that is more stable. And there is a range at which you get these glasses, but the phenomenon that is of interest here is that the rate of increase of the viscosity is tremendous. Let's say on a small range in temperature, the viscosity that is measured here in poise can jump 12, 13, 14 orders of magnitude. So for every practical purpose, the material is a solid. Now, the mechanical yield in an amorphous solid, I will now explain what is the yield. The first question that I got in this lecture is what you see here. For example, you have an earthquake. So an earthquake, the material yields and breaks. Okay, so yielding means that you apply a mechanical strain and the material is no longer able to react elastically, but actually it fails, it yields to the external strain. It can be very catastrophic. We had recently mudslides in California. There are many of these events that you're all familiar with, And it will be very interesting to make some progress in understanding this yield. Optimistically, if we really understand, maybe we can also predict or warn or find ways to prepare for events like this. It's not going to be the bottom line of this lecture. We don't know yet how to do it, but this is the general interest in this kind of problems. Snow, avalanches, etc. So all these are yield phenomena where a system has a increased strain and at some point it yields a phase. In technology, you have a yield, for example, in metallic glass. Metallic glasses are a family of modern man-made materials. It's very interesting. Metallic glass is made from a few metals together, not a single one. A single one always has a very strong tendency to crystallize. If you cool down copper, it will crystallize, no matter at what rate. But it was already understood in 50 years ago that if you take a binary mixture of metals, say copper zirconium, and you cool it very quickly, okay? In those days, what they did, they took a melt and they splashed it on a cold substrate. It will go through a glass transition and will not crystallize. These days, our colleague from Caltech, Bill Johnson, is making a lot of money selling metallic glasses to various companies like iPhone, in which they use 5 or 6 different metals, and then you don't need to cool so rapidly. In the old days, they had to cool 1 million Kelvin per second. Now, 1,000 Kelvin per second is sufficient to get very nice metallic glasses. Now, if you press one, if you stress, this is a uniaxial stress. By the way, why do I have to shout when I have this? I don't quite know. So let me see. I count on Okay. Great. So if you take a rod of metallic glass and you uniaxially stress it, at some point it fails by creating what is known as a shear band. So you put a uniform shear or a uniform strain, and at some point, miraculously, all this uniform strain is localized in one plane, and at that point, the thing breaks. And the question is why? How can we understand it? What is the reason for finding a phenomenon now that goes over the whole scale of the system here? You also may notice that the shear band is at 45 degrees from the uniaxial strain, and this is also something we like to understand why it forms in a way like this, etc. So many amorphous solids fail mechanically in the same way. What do I mean by this? So now imagine that to do things in an organized way. Let us imagine, this by the way from numerical simulations, that I take a amorphous material that I get by such a process of cooling a melt through the glass transition. If you now increase the strain, and the strain now is parameterized by a number gamma, I'm now doing a simple shear, so a material of this form is going to go to things like this, and gamma is this ratio, this over this, so the strain over the height. So gamma measures how much I make a strain. So as I say, for small gamma, you always react sort of elastically. So you have a linear slope. This is the stress, the internal stress that is being created in the material. And the slope here is known as the shear modulus of the material, very old and well-known object. And now the point is that when you increase the strain, at some point, the system fails. So this is the failure or the yield in the sense that at some point, the stress cannot increase a given value. And if you do it in strain control, if you just control the strain, then now the system will flow and will not be able to increase the stress. Now, I have to say that I spent personally, I don't know, maybe some 5 years of my life, not all the time, but sort of on and off, trying to understand what is the difference between the properties of the material here in the failed phase to the properties of the materials in the elastic phase. How does the system know that here you can increase the strain and the stress increases,
Whereas you go here, you increase the strain, the system is unable to increase the stress. It turned out this was the wrong question. And it's not a question, the issue is not, as I'm going to argue to you, what is the difference between the properties of realizations here and there, but the issue is what is the number of allowed configurations to the system. And I'm going to argue to you that the yield has to do with opening up a vast vista of possible configurations, many of them unstable, whereas when you're here, you're very limited to a small spectrum of configurations. But we'll come back to this issue. So, as I say, what we were interested in is what's the difference in the material before and after the yield. Now, the observation is that the same basic phenomenology appears irrespective of the microscopic interaction potential. Whether I do it on the computer with Lennard-Jones interactions or with soft spheres or with hard spheres or whatever, if I do it in experiments with metallic glass or polymeric glass or structural glass, always you have the same phenomenon that I showed here, that you have an elastic or quasi-elastic regime, and then a yield, and from that point on, the system cannot increase its stress when you increase the strain. So we are really seeking a universal language to describe this transition. We cannot expect to have an interesting answer that depends crucially on the details of the microscopic interaction, because it is a phenomenon that occurs in such a wide spectrum of materials. So that's the aim. So let me start by reminding you what is the difference between elastic and plastic. So what is plasticity? And first, let me remind you what is plasticity in crystalline materials, because that problem is understood, already understood from the middle of the last century, the 20th century, where one of the advances of condensed matter physics, solid-state physics, was understanding that if you have a dislocation in a crystalline material, if you now put a strain, a dislocation will glide. And the glide of the dislocation is an irreversible process, and energy is being used for this, and this is a plastic event. So everything where energy is lost is plasticity. Elasticity is always reversible. You can strain, and if it's purely elastic, you can go back and you gain all the mechanical energy when you go back. Not here. If you have a dislocation, it moves, etc. So this has been already understood many years ago, and even towards the last part of the 20th century, even when you have a field of dislocations, people have made progress in understanding what is going on. But it's clear that plasticity in crystalline materials is dominated by dynamics of dislocations. If you have a glass, it doesn't have any long-range order. I remind you, you get the glass from cooling a liquid, and there's no phase transition. So the structure of the solid is amorphous as the mother liquid. So there's no long-range order, and therefore you cannot define a dislocation, because you need to have the long-range order with respect to which you can define a defect. So then you need to discuss what is plasticity in a entirely different way. So let me spend 3 minutes on what is plasticity in amorphous solids. So that's the question. And the understanding started with a nice paper by Malandro and Lux in 1999. I learned this really from Anaël Lemaitre, who is my colleague, around 2006, 2007. And then we developed this a little bit in a way that I'll explain now. So imagine that I'm looking at a, let's say, numerical simulation, and I have a material that I created this way. Every particle will have a coordinate. So let me denote by I, the ith particle, I going from 1 to n. And the coordinate xi, when I make a strain, for example, if I do this simple strain, then there are two components to the response of the system. One is what I do, what I decide to do. And that is identified here by what we call the affine transformation J. For example, in this case, in 2D, I can say that xi, okay, the coordinate x now, not the vector x, is going to xi plus delta gamma yi, and yi is going to yi. Say in 2D, in 3D, zi is going to zi, and then you just move and make a simple shear. Now, the fundamental thing about the difference in amorphous solids and crystalline solid, if you do such an affine transformation in a crystalline solid, that'll be it. The system, some bonds will stretch, some bonds will quetch, but the system will remain in mechanical equilibrium, especially if you have a point symmetry in this crystal. Now, in an amorphous solid, as I'm going to argue to you, there's always, once you have applied a affine transformation, the system is not going to be in mechanical equilibrium. Here's an example. You have here a typical sort of amorphous solid made from a binary mixture of particles. Here, these are not real spheres. These are Lennard-Jonesians. The size here just represents the range of interaction of the Lennard-Jones potential. And you have two types, small and large. Okay, so now I'm going to do a simple shear. So now I'm going to show you with these arrows how much I'm going to do the affine transformation. So every arrow here will tell you how much the particle is going to move. And I start from a situation of mechanical equilibrium. And now do it, okay? I did it. And now I'm asking, are the forces on every particle still zero? Because mechanical equilibrium requires that the total force on every particle is zero. Otherwise, they're going to move. So these are the forces that have been created in this particular game. So now the non-affine response is going to annul these forces. So I just did it, okay? So this thing was annulment and rearrangement of the particles by a non-affine response that is always there when I have an amorphous solid. It can be reversible or irreversible, but it's always there because the system has no point symmetry. So if you do an organized affine transformation, the system will create forces on the particles. So can I now estimate how much non-affine will be? Very easily. Because now let us see. I started in the system with mechanical equilibrium, so the forces Fi on every particle are zero. I ended up with a system in mechanical equilibrium, so the total derivative of the force Fi because of this change in gamma that parameterizes J is zero. Okay, so I started at zero, ended up at zero. Gamma parameterizes how much this affine transformation is there, so the Fi d gamma has to vanish. But Fi, if I have a Hamiltonian system, is minus du dri. So this is the total energy of the system. Du dri is the force. So I now have a condition minus d gamma du dri 0. And since I have a linear relationship between xi and ui, I can also take the derivative with respect to ui with impunity. So now I have a strange double derivative. One is a full derivative and one is partial. So I need to interpret it. What does it mean? So here's the interpretation. So firstly, of course, the energy itself is directly affected by the gamma. I make a change in the positions of the particle, an affine change. The energy is going to change. So one contribution here is going to be the second partial derivative of u with respect to gamma and ui. I have one partial to ui. There is a direct dependence on u on this gamma, so I have a second derivative here. And then the ui itself, how much non-affine response is there, is also going to depend on this gamma. If I do small one, the non-affine is going to be small. If I make a large strain, the non-affine is going to be large. So I have a dependence of ui. So I now can get the chain rule and say that the second contribution is due to the dependence of ui. So I get the discrete du duj dui dotted into duj d gamma. So here is the contributions to the dependence of u on gamma. Now, this is a very well-known matrix. It's the Hessian Matrix, Hij, that I'm going to use in a moment. Here is a vector because it has only one index, so let's call it psi I. So it's known in the literature as the non-affine force, and now all this thing has to be zero. So this gives me now an opportunity to solve how much non-affine response I got. How can I solve? I have to invert this equation. So I have to now take the psi I to the other side, compute Hij to the minus 1, etc. But here's the danger. Can I always do it? Well, that depends. If the system is stable, by the way, this is a real symmetric matrix, so all its eigenvalues are semi-positive, so I can invert if there is no zero. But of course, I cannot invert if I get a zero. So what is the situation? The situation is really very interesting. Always when you start in equilibrium, before you strain, it turns out that all your eigenvalues are positive. The system is stable. Okay? So here is an example of the eigenvalues of the Hessian matrix as a function of the relative strain. And you see, you start, they're all positive. Now you increase the strain. Many of them don't care. They change a little, but they don't, nothing catastrophic. But every now and then, catastrophe. An eigenvalue, boop, goes to zero. This is an instability. This is a plastic event. This is where something interesting happens. So now, let us assume that it didn't happen yet. And I can then invert the equation that I discussed before. So I now solve for duj d gamma. And here it is, dui d gamma is minus hij to the minus 1 xij. I can now expand xij in eigenfunctions of h. So I have now the sum on the eigenfunctions k, psi k, lambda k, and this is the component of psi on that function. And now if I have the situation that one eigenvalue goes to zero, then when it's close to zero, this sum is going to be dominated by one term. We call the eigenvalue that goes to zero lambda p for plasticity, and then this is be dominant, and then the non-affine contribution is going to be proportional to the eigenfunction, psi ip. Psi is the eigenfunction of h. Okay, so you have here a matrix, okay, hij, symmetric, real. It has eigenvalues, eigenfunctions. So I'm defining the psi's as the eigenfunctions, okay, and they go with an index k. The I is for the particle I. And now the lambda k are the eigenvalues because I have h to the minus 1. Okay? So one term is going to dominate, and I get a prediction that the non-affine contribution here is going to be proportional to the eigenfunction of the Hessian that is associated with the eigenvalue 0, that goes to 0. What this eigenfunction looks like? Very interesting, because when you're here, it turns out all the eigenfunctions are delocalized. Okay, not a big surprise. For those of you who are familiar with the Anderson localization, you know that eigenfunctions in disordered systems can be localized at the high energy end, but never at the low energy end. These are the low lambdas. These are the small lambdas. But here it is. The second derivative of the Hamilton. Here it is. So it's the second derivative of the energy with respect to the positions. Yeah, or R. It doesn't matter. So you have an energy, U, which is a function of R1, R2, R3, Rn, right? Okay, that's the energy of the system as a function of the positions of the particles. Okay? And now this is the second derivative, d squared U, dri, drj. Okay, that's the Hessian matrix. Very simple. Of course. But this is not these eigenvalues that are going to 0. So these are, these are in the Debye modes, etc. I mean, there is elasticity. Okay, so if you bang it, it will have sound. But I'm now focusing on those eigenvalues that are associated with the plastic instabilities. And what I'm trying to argue is that you have a very interesting localization phenomenon that has never been discussed in the context of the Anderson localization. In what sense? That here, what it is. So you can show first that when an eigenvalue of this associated with this eigenfunction is going to 0, it always does it in the square root singularity. The reason because it's a saddle node by bifurcation. But the more interesting thing is that, for example, in 2 dimensions, a delocalized function gets localized. Okay, and this is the fundamental plastic event that you see in an amorphous solid. What is the event? Some particles are streaming out, some particles are streaming in, and you get a local release of stress. That's plasticity in amorphous systems. Now, this object is an interesting object because it's quadrupolar, and I'm going to say a few words about the nature of this eigenfunction. So, in fact, it's very interesting that in the 1950s, there was a beautiful paper by Mr. Eshelby, who asked a very different question about materials, elastic materials. He said, let me take an elastic material, let's say 2D, let me cut out a circle. Take it out, distort it to an ellipse, and stick it back. And he asked, what is going to be the displacement field that is going to be associated with such a deformation? Turns out it's the same. It's the same, and there is a deep reason for this. The reason is that this is the cheapest way, and I'm not going to prove it, but believe me, this is the cheapest way to release stress locally by doing what some people call a T1 event. That is to say, some particles are going in, some particles are going out, and we have an analytic understanding of the form of this we're going to tell you in a moment. Okay, so the point is that plasticity is the appearance of a plastic event through an eigenfunction that looks like this. Some particles are going out, some particles are going in. It's known today as an Eshelby quadrupole, but then there is something else that is happening when you increase the strain further. Am I clear? I mean, are you following me? What it is? Ask me. Okay, let's go slower. I have time, so please ask me. So,
on your next picture, what is drawn?
Here,
Drawn as a-
this is the eigenfunction that is associated with the eigenvalue that is going to 0. Now you see, these are particles. The eigenfunction is kth eigenfunction, but has an index I. Index I is for the particles, yes? So it tells you how every particle is, this is the UI. So this is how the non-affine response is looking. When you take the affine transformation, after you reached again mechanical equilibrium, you now take the position of all the particles, you remove the affine part, this is what remains. It's a non-affine part. But the non-affine part, as I prove here, in this, is dominated by the eigenfunction that is associated with the eigenvalue 0. Okay, so we just put a finger on what a plastic instability is, and it has to do with such a quadrupolar T1 process. Now, when you increase the strain, at some point, there's another transition. Suddenly, and this is the yield, they appear in a series. So at some point, you get that all these guys are appearing one after the other, and they're sitting in 2 dimensions in the line, and in 3 dimensions on the plane. This is the shear band that I showed you before. So this is going this way, this is going this way. But if when I had a single one, which is the plastic event, as long as I'm not yielding, the displacement field is now falling as a power to infinity, now you get a global connection, because this goes out, this goes in, this goes in, this goes out, and this now is going to organize the displacement field such that it's going this way here and this way here. Okay, that's the shear band. Okay, so this is how you understand what happens. Now I have to explain to you why you get this concatenation, why you have this organization, and I'm going to explain this in 2 ways. One, I'm going to explain this in terms of energetic considerations, why it's the cheapest way of doing this, and another way I'm going to explain this in terms of statistical mechanics, because there's an interesting question here from statistical mechanics. You get a system spanning event, so you have a correlation length that spans the system, and the question is why. Okay, so the energetic argument. It's a bit involved, but it's not really involved. So I'm going to explain this very easily. So the Eshelby paper that I mentioned before gives us an analytic form for the displacement field that is associated with this single guy. And it's written here. You don't need to look at the details. In 2D, it decays like 1 over r squared. It has 2 parameters, which is the eigenstrain epsilon star and the so-called Poisson ratio nu and a core size A. Okay. Now, if you want the details, they are here. So now I want to ask, imagine that many of them want to come together. Okay, so I have some density, or say I have some number n. I can write down, because it's a linear elastic problem, I can add up all the contributions to the energy. So if I have a strain, okay, and I have a stress, then the material itself will have the stress times the strain, the general overall stress and strain. You have a contribution of the overall stress with the eigenstrain of each of the Eshelby, sum from I to n. So I'm assuming I have n such Eshelbys, n quadruples.
That's a big strains. You apply still linear.
It's absolutely linear, in the sense that if you look locally, you have a shear modulus and everything is fine. Yeah, it's perfectly okay for these things. You just need to understand why they now organize in such a strange way, but it's legal. That is to say, as long as you are not at the point there, so if you are looking at the stress versus strain, then you have these localized fall, and then boom. So all these regions are still linear, and then you have this yield. Okay, so it's a proper thing. It's not dangerous.
You assume that displacements are small with respect to some new position of equilibrium or something. Because linear theory requires that strains should be small.
The question is, what do you mean strain? Because strain is not a state variable. Strain is always with respect to a reference. Okay, so the steps here are small. The steps here are small, and it's always with respect to the last equilibration. So I'm doing it in a quasi-static way. So after every such thing, you're back in mechanical equilibrium. So the answer is yes.
But then your elastic constant becomes state dependent.
It's an interesting statement, and the answer is no. So actually, I mean, these are issues that we thought about a lot. You can argue that, the effective stress versus strain, if you do a average over many systems, looks like this, and you could say so. But in fact, it's made from linear drop, linear drop, linear drop, and the linear one doesn't depend on the state where you are. These are details. I mean, I'm trying to give you the picture, and we can discuss with pleasure if you want, and I can convince you that the details are okay. So I started just to describe what are the objects that come in. Basically, it's the background elastic energy, it's the elastic energy of the background with the Eshelbys, it's the Eshelbys themselves, that is the sum over all of them of the stress versus strain, and the Eshelby interaction, epsilon of one on the sigma of the other, blah, blah, blah. And now you take the whole thing and you say, let me minimize it. Because I want to find what is the cheapest way to put in n Eshelbys into a thing. And you find, amazingly, that the minimum is obtained when they're all sitting in line and with the same phase. So what I showed you here. So this minimizes, as the single one minimizes the energy associated with this loss of some stress locally, this minimizes the energy that it costs to do this globally. And once you have this, you can write an energy, the elastic energy associated with the density and with the strain. And this function has a nice form in the sense that you can show that it always increases as a function of the density when gamma is too small. So when gamma is smaller than some gamma yield, the energy is increasing with the density, such that the only solution is a zero density 1, such Eshelby is what we see here in this regime here before we yield. But at some point, when gamma is increasing, you get a zero slope, and then you can have a new solution, and this gamma yield can be found analytically and has to do with the epsilon star, the eigenstrain of the Eshelby, and the Poisson ratio, and these numbers are in very, very good agreement with what you see in experiments and in simulations. So basically, this is the energetic argument. The energetic argument is that says that it is cheapest to make a big stress drop by doing this shear band. It's cheaper than any other thing that you could do. So this is a natural thing for the failure from the point of view of energy. But now I want to turn to the statistical mechanics. And I want to show you that you can understand this also as a critical phenomenon or as a phase transition picture. Now, let me just say that some 20 or 25 years ago, maybe 30 even, I don't know, Pokowski probably remember this, people were interested in the appearance of these long-range phenomena like in earthquakes. What is the reason that you have suddenly an infinite correlation length? And there was a Danish colorful physicist by the name of Per Bak that started to talk about self-organized criticality. You all remember this? Yeah. Now, I was never clear what is a self-organized criticality. What does it mean? And what I'm going to argue to you today that we understand what it is here, and there's nothing to do with self-organized. It's really not self-organized. You force it by your straining, but it's actually a spinodal criticality that I'm going to flush out now. So, in order to explain this, you have to construct an order parameter that will do the job. Now, you have a disordered system. You have an amorphous system. So how you construct an order parameter for a system that has no order? And this is, you do by going to talk to Giorgio Parisi, who is an expert in dealing with amorphous systems due to his long history in spin glasses. Turns out that some ideas can also be applied for the case of amorphous solids. So let me introduce to you the ideas of replica. So replica are obtained when you have two replicas of the same system. So imagine that I have one system that I'm going to call 1, and another system I'm going to call 2. And these are the positions Ri, this is classical physics, so are distinguishable. Ri in the system 1, I going from 1 to n, and these are Ri in the system 2, where I is the same I. So I'm asking the position of the same particle in this replicum and in that replicum. And now I can introduce the overlap function. So the overlap function, Q12, this is now a step function, theta. So I'm looking at the distance between the position of the particle I in replicum 1 and the position of particle I in replicum 2. And the distance here, I now compare it to a tolerance A. A is going to be of the order of a half of a third of a typical potential length. So for Elena Jones, it's going to be a third of its extent. Now, what will it do? If it's the same, if these replica are the same, if Ri are the same in the two things, then this is always 1. So you're going to have n ones over n, so Q12 is going to be 1. If these replica are very different in the sense that Ri in replicum I and 2 are separated more than A, then the step function is going to give you 0, and Q12 is 0. So this gives you a way to compare the closeness of two amorphous replica. Okay, and that's going to be the order parameter in our theory. So let me now explain to you how we do this on the machine. So imagine that you start with the glass former in the liquid state at some temperature above the glass transition. Now you quench it to temperature 0 using molecular dynamics or whatever you want to do. Now you heat up to a low temperature. In our case of Lennard-Jones, in Lennard-Jones units, it's T of the order of 0.2, but it's much below the glass transition. Now, at this point, you pick one configuration. You run your dynamics, you pick a single configuration, and you freeze the particles, and you randomize the velocities. Let's say 500 times. Of course, this is arbitrary. It could be 1,000 times or 300 times. Okay, and the randomization is done with the Boltzmann weight at this temperature, 0.2. Okay, so these are legal configurations at that temperature. Depends. We do it up to 50,000 particles. Depends. I'll show you also system size dependence in a moment. And now when you have done it, quench again to T equals 0. What this creates is what we call a patch of configurations. They're not going to be one on the other, but they're going to be close because they start from the same physical positioning, but with different velocities. So when you quench to zero, they're going to move a little bit, and I'm going to show you in a moment that the overlap is high, of the order of 1. Now you can repeat the whole procedure, let's say 100 times. Again, it's arbitrary, 200 times, 300 times. So you can make so many patches. Okay, and now you see you can measure the order parameter as a function of your strain. And that's a very crucial diagram. Because you see, this is the stress versus strain. You see this is where the yield is, roughly. And this is how the overlap looks. It starts at the order of 1, and then as a function of the system size, 500,000, 2,000, 4,000, 10,000, etc., you see that Q12 is going to 0 when gamma is increasing. The speed or the slope at which is going to 0 is a function of the system size, and in the thermodynamic limit, we argue, is going to be infinitely fast. For example, you can do this quantitatively. You look at the maximum of the slope. So you look at each one of these guys, you take the derivative, you find the maximum of the derivative, you call it S. The maximum one, you now plot S as a function of n, and you see that it's a power law that is increasing. That is to say, this is very likely to go to infinite slope at thermodynamic limit. Yes? On each one. So you have all this replica. You take every replicum and you strain. And now at every strain, you compute the overlap. Not with a 0 strain, but all of them at that strain value. Okay? And you find that they're all together before, and now they're separating dramatically, and I'm going to say more about this, when the yield occurs. And this is going to be related to what I told you before. There is an opening of a vista. It's what I call now stressed ergodization, but I'm going to come back to this. Yeah.
I think the question is,
Yeah.
the fly stress after the quench?
Strain.
Straight. After the last quench?
Okay. All the application of the strain is quasi-static. I do a small step of strain, and I allow the system to energy minimize.
It doesn't change the temperature.
Temperature 0.
Okay, so you
I said the all quench to temperature 0. This is a 0 temperature theory. Okay? And I'm going to say something about the finite temperature. Okay, but at this moment it's a 0 temperature theory. Okay, so as you see, this is becoming sharper and sharper. Now, I'm coming back to the comment that I said, that the yield is really stressed ergodization. This is what we're missing in understanding, really, when I was trying to figure out what's the difference in the properties. This was the wrong question. This is the essence. So I'll show you here. Imagine that I look at all my replica. This is the stress versus strain. And I ask how many of the replica the overlap function has gone below, let's say, 0.8. Okay, arbitrary can be 0.9. It doesn't matter. And you see that all of them, that all the 50,000, I have 100 patches, so 500 each. All the 50,000s lose their overlap around the yield. Okay, so this is an opening up in the sense that all the replica are now seeking life in a huge vista of possible configurations that were not available when you were in the elastic regime. Okay, since we have enough initial configurations, we can consider now the probability of the order parameter average over the realizations. What you see is the following. So now you look at the probability as a function of gamma of this Q12. And this is for various values of gamma near the yield. What you see is that before the yield, let's say at gamma 0.08, you have a big peak at the order of unity, and then it falls down. When you go beyond the yield, you have a big peak at small q12. Okay, so you have already yielded, and there is a point in the middle where they are sort of at the same height, which you would accept as a first-order transition. So it looks like a phenomenology of a first-order transition. In the thermodynamic limit, you expect that when one maximum is just a little bit smaller than the other, boop, it'll jump there. This is sort of the Maxwell construction. And the phenomenology of here, you see within the replica theory, is that of first-order transition. But then you can ask me, wait a moment, you were looking for an understanding of an increase of correlation length. System spanning, shear band. First order transition generically does not have an increase of correlation length. But now I want to point out to you the green curve. You see the green curve here? So this is slightly after the first order transition. You have here a flat region. Now, if you say I have a PDF, if you had a free energy, it'll be the logarithm of the free energy, then you have a region of flatness here. It means that you have a flatness in the derivative of the free energy with respect to the order parameter. That's a spinodal point. That's a spinodal point like the one that you have in usual first order transition, like the liquid gas, etc. So when you just go to the limit of the availability of two phases, and you just go to the one phase. So the last thing that I want to tell is about the paper that was published recently with Giorgio. So now we just want to finish and understand the appearance of a increased correlation length, and with that I will leave you. So in order to see this, you need to just make a little generalization of what I told you before, of taking now the overlap function and make it localized. So I'm now localizing what I had before. I had the step function L now. It was A before, RIA minus RIB, 1 and 2, A and B. And now I'm calling this delta R minus RIA. So I want to localize this at a point R. This doesn't matter if I do it RIA or RIB, because this is anyway 0 if RIA and RIB are far from each other. So I'm localizing this. And then there is a whole lot of theory here that I'm not going to bother you with that is very helpful to talk to Giorgio about, because it has been done in a different context. And there are well-known correlation functions that you expect to see the increased correlation length. There is the so-called longitudinal correlation function and the replicon correlation function, the gamma 2 correlation function, etc. I'm not going to bother you a lot. Just as an example, the gamma 2 is a simple second order correlation function of the overlap function Q minus the mean of QQ. This is a slightly different one, which has A and B and A and C and C and D, so more replica are involved. Let me point out that these look to the eye as 2-point correlation function. In fact, they're 4-point correlation function, because already the overlap function itself has 2 particles involved. None of the interesting phenomena in disordered systems are apparent with 2-point correlation function. I'm saying this in parentheses. You always have to go to 4th order or higher. And then just to show you how it works, so you can now define the susceptibility, etc. And here is how, for example, the replicon correlation function is behaving as a function of the distance from the yield, or from the spinodal point, I'm sorry. And you see that the correlation function has an increasing correlation length that you can plot, and as a function of the system size, this for small system size is a small effect, large effect for 4,000, a big effect for 10,000, and you can plot the correlation length as a function of the distance from the spinodal, and you see that it's increasing as a power law. We do not understand the power at this point, 2.4. We're trying now to develop a theory for understanding the power. It's not easy. But I think it's possible, so this is still for the future. And now I just want to finish with a short comment that all this is working so nicely because the temperature is 0. What I'm trying to say, you see, spinodal criticality is known for a long time. Everybody knows that near the spinodal, the free energy has a flat region with respect to, in the derivative with respect to order parameter. No one has ever seen a spinodal criticality. And the reason is that when you have temperature, it always jumps before you go to the spinodal. You have the Maxwell construction. Here we are at temperature 0. So temperature 0 allows us to stabilize a spinodal that is very difficult to see otherwise. So I just want to finish by making the caveat that if you have thermal systems, then things can go berserk. For example, this is just a copy of what I showed before, the 0 temperature. At the temperature of 0.1, you already see that things become sort of more questionable. The nice point of the phase transition here is a bit smeared, and when the temperature is somewhat higher, 0.2, you lose entirely the phase order transition. You get a continuous change, and anyway. But just wanted to say this, but is this not a disaster? Because we know that real glasses, like metallic glasses, the temperature the room temperature is much, much lower than the glass transition temperature. So I think still this is all rather relevant. Thank you very much for your attention.
Questions? What was the logical step between this excitation and the replica?
So, I mean, we needed a replica in order to understand. I mean, you can say, if I accept that I have a appearance on an infinite scale of all these quadrupoles, and I can, from the energetic argument, explain where it's going to happen, etc. But why? Okay, so I needed this kind of theory to offer a way of thinking why there is an increase in correlation length to begin with. And what we say that there is a spinodal point here that is associated with criticality. Now, this is an issue, you see, because I'll tell you why this is an issue. Because if you do a simple calculation, random field Ising model, say, what everybody knows how to do, with disorder, and you ask yourself, there is spinodal points there. Is it critical? No. The disorder destroys the criticality. But you need to do something more difficult, because here, here you have a situation, you have a long-range interaction due to elasticity. And on top of it, the critical nucleus, which in random field Ising model is spherical, is actually extended. That's the critical nucleus. So we don't have yet an independent theory, solid one, to argue that the spinodal is critical. Everybody agrees now. It was a little bit of a shock at the beginning, but now all the people in the subject believe it's the first order, there's spinodal, etc. The argument that remains is, can you show theoretically that it's a critical spinodal, that you really have an increase in correlation length? And it's theoretically a very interesting question. I was just yesterday, I was in Santa Barbara, and I talked to colleagues like Giulio Biroli, and these people were very much interested in these things. And we thought maybe one should look at a anti-ferromagnet with long-range interaction to see whether spinodal with disorder is going to still be critical. Because I think the long-range order is crucial. So there are still issues here. So what I'll show you is a numerical proposition that at least the replica approach indicates that there is indeed an increased correlation length at the spinodal here. So.
In addition to the question of the step, I would like to ask you about approximately the same. You can, in your Born parameter, which you
It's not mine, it's Giorgio's. Actually, Fanton. Okay. It is different, but it's the idea is there. Yeah.
So you compare the displacement of two different systems.
Yes. The distance.
They are identical by their properties.
Exactly.
But they are different.
Yeah, it's the overlap between them. Yeah.
But what you in reality need is to describe the property of one of them.
Why do you think so? Why do you think?
Why one system obeys that?
Well, that's a very interesting question. And of course, it has to do with the fact that when you go to the thermodynamic limit, then at some point you'll have many, many similar systems that are interacting. Okay. So that's the whole tenet of the replica approach, right? That we are using here small systems, 10,000, 20,000, and we replicate them in order to come closer to understanding what a system in the. You can argue this. You can argue. It's a fundamental assumption. It's a fundamental assumption of the replica theory, which so far seems to be rather useful for discussing systems that are disordered. But you're absolutely right. The replica theory, I have to say personally, I was very suspicious of replica theory for a long time. I fell in love with this because it seems to do something interesting where I couldn't do it in any other way for this particular problem. Now, maybe I'm being led by my own enthusiasm, but I think it's interesting. Go ahead.
We understand this correctly. What you actually measure is that you start with almost identical system, right? You change them, and then you measure how far.
When. No, not just how far. When they are going to be unhappy to be close by. So you see, so
they can't go to different directions.
so the point is that you see, I started the discussion today with the following question. I started with the question, what is the difference? Okay, what is the difference? Where were we? Right, I really started with saying, what's the difference between the physics here in this regime and the physics in this regime, right? That was the thing that I wanted to understand because it bothered me, okay? Because I wanted to understand why here the system cannot increase its stress, okay? And now I understand that there's something fundamental different in the sense that a system here is confined. Now, to come back to Professor Pokowski's question, the single system is confined from itself, Now, you can see this in the replica, but it's confined within its, how do you call it, its local minimum, okay? And it doesn't run away from it as long as you don't come here, okay? With the replica, you see that they just disappear from each other, but also one system disappears from itself, okay? So that's the way that you want to think about why the replica represent the physics of what is happening here. You are creating, the system in equilibrium before you strain it is limited to a local region in its phase space. And it cannot escape by mechanical strain until the mechanical strain exceeds a threshold, which is called now the yield stress. And that, I think, is the main physics of the phenomenon here, and this is why the replica approach indicates what is happening here. Did I answer the question? Yeah. Sorry.
Okay.
No, you are the boss.
I have two questions.
Sure.
First is, how do you define your shear band? And are you defining it in such a way as a length scale? And if so, what sets the length scale?
Okay. Okay. So actually, the definition of a shear band, if you want, is a concentration of the uniform shear in a small region. Now, it's in 2 dimensions. It happens. It's of dimension 1 in 2D, and it's of dimension 2 in 3D. And in fact, the structure in 2D is very interesting because they sit on a plane, and the Eshelbys are sitting on a triangular lattice in the plane, which is something that we've shown. But the point is that it also has a width. Okay? Now, the width, nobody knows. Boss. Yeah. Yeah. So, for example, if you want to see, when you take a glass and you cool it down, you find that it becomes slower and slower. The viscosity is increasing, so to speak. Or if you want, the relaxation time is increasing. Usually, a relaxation time increasing is accompanied by increase of some scale, of some dynamical scale. So people tried for a long time to look at 2-point correlation functions and see when you cool down whether you get an increase in the correlation length. The answer is no. The breakthrough came when my colleagues who were there, I think Jean-Philippe Bouchot and Giulio Biroli, some of these guys from the Paris axis of evil, as I call them, they looked at 4-point correlation functions. And suddenly, poof, you have something. So you show that the dynamical correlation length of 4-point correlation function, 6-point correlation function is increasing when you go down. Now you could ask me why these phenomena are not apparent in the 2 points, and I wouldn't be able to give you a very convincing answer. But it seems like a fact that 2-point correlation functions in disordered systems, contrary to critical phenomena in order where the order parameter is obvious, you don't need to go to higher order correlation functions. Disorder, the definition of the order parameter already requires 2 points, right? So anything further is at least 4 points. But it's not a very deep answer, it's just a fact.
Also probably is the people
Yeah.
wish to deal with the average, not the some realization, but with the average. When you do this average description, the number of the rank of your correlation construct.
Yeah, but if you just compute the 2-point correlation function in a given realization, it doesn't grow in the glass formation when you go to, yeah. No, it doesn't. What can you do? Yeah.
Let's say this rearrangement bands that you have.
Yeah.
When they form, does it code for
They just appear. They appear in the numerics, they appear within the range of the energy minimization after a change of strain by some delta gamma. So you allow the system now to energy minimize, whoop, it appears. Yeah, simultaneously. It's not a dynamical thing. It's not an avalanche in the sense that one creates the other, creates the other, creates the other in time.
So one question is that is it possible that this mass rearrangement is rate dependent on how fast you're applying your stress?
It's a quasi-static calculation. So it's really, again, it's an eigenfunction, a new eigenfunction that appears with eigenvalue 0. So it's an instability. You see, it's an instability of the system. The Hessian responds with an eigenvalue that goes to 0, and that's the eigenfunction is associated.
If you go to continuum beta, the system losses its relativity.
What do you mean continuum? Without particles?
Yeah, if you want tomorrow.
I don't know. I mean, physics is discrete. Yeah.
So you said at the very beginning that this shouldn't depend on the microscopic structure.
Correct. Yeah.
But your Hessian was the derivative of the energy with respect to.
But it's any Hessian. But
But the non-affine response seems to depend on the microscopic structure.
No, it's an eigenfunction. So it's already, if you want, it starts as a delocalized thing, and it has to do with an instability of the system, on any scale. It's not because it's Lennard-Jones or hard spheres or soft spheres or whatever, right? I mean, you can do the same thing for any of these glass formers. Many models or many real materials will show the same thing. And I used the notion of the Hessian, but didn't put in any form for the energy. This is what confused Professor Pokowski said, but what is this Hessian, right? So, it's any Hessian. It doesn't matter what is the interaction that is involved.
Nonetheless, the use depends somehow on the structure.
No, the use, I'll tell you how they're going to be influencing. So the only parameters that you have are the parameters in the solution of Mr. Eshelby. So I told you that there is the Eshelby solution. So the Eshelby solution, which is this quadrupole, has a core size, has a Poisson ratio, which is of the material, and has the eigenstrain. So that depends the strength. That's it. There's nothing else. No. And so these are the material parameters that are going to appear. And, you know, like the Poisson ratio, it's not really, I don't know how to tell you why Poisson ratio is 0.3 or 0.4 if you change the Lennard-Jones length. You know, it's the material on the whole is determining it. So it's a very generic theory in some sense. You know, it doesn't depend on the details in the sense that it doesn't matter is it... No, my scale is on the particles, but the theory is on much larger scale.
On the size of particle,
Nothing happens. Yeah. So I'm saying I'm using the existence of the particles, but now I'm using eigenfunctions like the Bi. You know, the materials of the Bi are made of particles. But the Bi density of modes you compute from elasticity theory, right? So it doesn't matter. But, you know, you have a combination here of a theory that is based on the existence of particles, the only numerical simulations in the particles, but I'm saying that the theoretical thinking is independent of the detailed interaction, the detailed type of the interaction between these particles, as long as you're having a glass former of this type. Yeah.
Let's thank the speaker again.
Thank you.
Any further questions?